Okay. Let's get started again. We'll cover some techniques for hybrid memory systems, two major techniques. I'll give you the basic ideas, and I'll then talk about some flash memory scaling challenges, which is related to, even though flash is not an emerging memory technology, it's a non-volatile memory technology, and it's facing similar scaling challenges to DRAM. So we'll talk about some error correction mechanisms for flash that are cheaper than error correcting codes. And we'll conclude after that. I think it makes sense to not go further and start memory quality of service on Monday so that other people who want to see that topic will be here. Okay, this is basically an idea we've been examining to better manage hybrid memories. The key question when you have a hybrid memory system, and these colors are not coming out that well. I think this has a problem with not the red color, but it has a problem with the light colors. That seems consistent. The key question is, how do you place data between these heterogeneous memory devices? In addition to exploiting locality, how can we exploit the characteristics of these devices? The motivation is these devices actually have row buffers, and these row buffers that we've discussed a lot have implications on data placement. If you look at this, you have DRAM and phase change memory. DRAM is a small capacity cache, and phase change memory is large capacity store. They both consist of banks. This is true for all memories, and they all have row buffers. Each bank needs to have some row buffer to buffer the data that's actually sensed. And you already know about row buffers, so I'll go through this quickly. You get a row buffer miss if there's nothing in the row buffer, so you need to activate the row and access that data. Now that if you access some other data element in the same row, it's a row buffer hit, and it's much faster, right? And we've seen this many times before. Row buffer misses, slower. The key observation in this work is row buffers exist in both DRAM and phase change memory. They may not be of the same size, and actually we've examined a lot what should be the size of the row buffer in DRAM and phase change memory. And phase change memory, you can make it much smaller. That makes the memory much more energy efficient also. But the key observation is that row hit latency is similar in DRAM and phase change memory, because this row buffer is very similar in structure, or it can be designed to be similar. It's essentially an SRAM buffer, cross-coupled inverters. Right? Whereas row miss latency is small in DRAM because you access the array, and DRAM array access is fast, whereas it's very large in PCM. PCM array access is slow. So we're going to try to exploit this fact. And the key idea is to place data in DRAM if the data is likely to miss in the row buffer, if the data has low row buffer locality. And the reasoning is this miss penalty is smaller in DRAM, and if it's reused many times. Because we would like to cache only the data that's worth the movement cost of moving from phase change memory to DRAM. Because remember, phase change memory is main memory, DRAM is a cache. So if the data has these two properties, then we're going to place that data in DRAM. So it's a very simple idea, but it seems to work quite well. I'll show you some results. So I'll give you first just an example of what it could buy you. I usually like these examples that motivate why a mechanism works. Basically, let's say processor accesses these 4 rows, A, B, C, D. And let's say row A and row B have low row buffer locality. Basically, they frequently miss in the row buffer, but you do access them somewhat. Let's assume that you do access row A and row B a lot, but they miss in the row buffer. Row C and row D, they have high row buffer locality. They frequently hit in the row buffer. Let's take a look at two cases, which is, one is the state of the art. You have a caching policy that's not aware of the existence of this row buffer locality differences. And we'll also look at a case where you have a policy that's aware of that row buffer locality. First policy, if you have this policy, it could place rows that have high row buffer locality in DRAM, and it could place rows that have low row buffer locality in phase change memory. Basically, you cache these rows instead of these rows. That's possible. Right? Let's take a look at this access pattern to main memory. Basically, you have accesses to row A, B, C, 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 A, B, dot, dot, dot. And we're going to look at the timeline of accesses, how long it takes. Remember, the high row buffer locality accesses C and D are accessed in DRAM. Basically, low row buffer locality accesses are accessed in phase change memory, and they keep conflicting in the row buffer. When you access A, you bring it into the row buffer, and then you get a row conflict, and then you get another row conflict, another row conflict, another row conflict, and assume that these are writes. Basically, keep thrashing the row buffer in phase change memory. As a result, whereas in DRAM you get a lot of row buffer hits, because these have high row buffer locality. As a result, the stall time is 6 device accesses in phase change memory, device meaning the memory array. With the row buffer locality aware policy, you would place these rows in the opposite manner. Basically, low row buffer locality rows would go into DRAM, and high row buffer locality rows would go into PCM. Right? That simple idea will make a difference. This way, you can access data at lower row buffer missed latency of DRAM, because these will keep conflicting in DRAM, right? The same conflicts will happen, but except that they'll happen in DRAM. Here, the same row hits will happen, except they won't matter. They'll be similar to PCM. So if you look at this, this was the previous case. If you place the data in a row buffer locality unaware way, and this is the current case. DRAM contains rows that have low row buffer locality. As a result, you get the row conflicts in DRAM and row hits in phase change memory. And if you look at this, phase change memory accesses are much shorter now, right? The limiter is really the DRAM. Stall time is 6 DRAM device accesses, row conflicts, instead of 6 phase change memory device accesses. So this is much shorter.
Here you assume that both devices have the same length of row buffer memory. Does this row array must be the same size?
No, we don't assume that. We just assume that these will be hits. So it may hit in a smaller array. That's right. In actually our evaluations, we assume that the row size of phase change memory is one-fourth of the row size of DRAM. That's right. Yeah, based on our previous results, right? So we'll assume the same thing, one-fourth difference. And this will still work pretty well. And we've looked at, actually we have a short paper, a technical report that discusses the implications of row buffer size and memories. I did not assign that, but I can send that paper. That is an extensive evaluation of what should the row buffer size be. And smaller row buffer size is a good idea in phase change memory, so we're not going to change that. And you'll still get good hits with a smaller row buffer size. Okay, basically you save cycles. Right? So let's take a look at how you can implement this. What are the mechanisms? Basically, for recently used rows in phase change memory, we're going to have a mechanism that counts the row buffer misses. So I guess one mechanism that's not implementable is for every row in memory you have a counter, right? That's not a good idea because that consumes a lot of hardware. And you need to have this somewhere in SRAM, probably. For recently used rows in phase change memory, we're going to count the row buffer misses as an indicator of the row buffer locality. So we're going to have that count. And if we're going to cache to DRAM rows that have misses that are greater than a threshold. And these row buffer miscounts are periodically reset. We only cache rows with high reuse. Basically, if a row has high reuse, it'll accumulate that count again. Right? That's how we pick rows that cause frequent row buffer misses as well as high reuse. Now we also adapt this. We have a dynamic policy which actually adapts this threshold dynamically to workload and system characteristic. And there's an interval-based cost-benefit analysis to see what threshold works well. That's relatively simple. And I'll refer you to the paper. There are a lot of similar policies that are employed. This is not the most novel policy in the world. Okay. So how do you actually keep track of this frequently used rows and their number of misses? Basically, we have a statistics store in the memory controller that looks like a cache. And the input is the row address. The output is the row buffer miscount. Basically, you cache the recently used row addresses and their miscounts. And we found out that a statistics store that is less than 10 kilobytes achieves system performance that's within this much of an unlimited size statistics store. So there's a lot of locality in the system, and you capture that with a small statistics store. Let's take a look at the results of this policy. So we have, again, a similar simulator that we're happy to provide. But basically, this actually can simulate a lot of the workloads. And these workloads are traced. Some of these are traced from big applications like TPCC, or online transaction processing, and web servers. And we're going to have a system with 1 gigabyte DRAM and 16 gigabyte phase change memory. And 4 kilobyte migration granularity. But we're going to assume that all workloads actually fit in memory. So we're not going to have benefits actually, I'll get back to that when I talk about it, comparison to DRAM. So there are several comparison points. One is DRAM is every comparison point DRAM will be a cache, and conventional LRU caching is one comparison point. Basically, this is dumb caching, and it actually doesn't work. That's not a good idea because there's too much movement between phase change memory and DRAM. Freak is the access frequency-based caching. This was proposed in HPCA 2010. Basically, the idea is you somehow figure out what is the frequently used data in a probabilistic way and place that hot data in the cache. And cache the DRAM rows that have accesses greater than a threshold. This is not aware of the robot locality. You can actually adaptively change that threshold, and we actually adapted our algorithm to do adaptive changing, dynamic threshold adjustment. This is still not robot locality unaware. And we also have the variance of our mechanisms that's aware of robot locality and also dynamically change the threshold. These are the results. We have some server workloads, some cloud workloads that are combinations of workloads, and the average across them. This is the normalized performance. And the baseline is this, let's see, frequency-based caching. Actually, baseline is the DRAM LRU caching. And frequency-based caching actually improves performance a little bit, but not that much. So overall, the performance improvements are greater than 10% compared to frequency-based caching, which is the state of the art. So the reasons of performance improvement, you get increased robot for locality in phase change memory by moving low locality data to DRAM. The second is you get reduced memory bandwidth consumption because you have stricter caching criteria. And this is very important if you have a system where you're going through the bus, going through limited bandwidth to transfer data between DRAM and phase change memory. Because this bandwidth is very limited, right? You don't want to do movement unnecessarily. And this bandwidth is very limited regardless of however you design this, right? You could put phase change memory here and have special connections here. This bandwidth is still limited. Okay. And the third benefit comes from, because we're actually distributing data between DRAM and phase change memory, we have more balanced request load, it turns out. Instead of accessing a lot of data from DRAM. For example, if you use LRU-based caching, your request load is less balanced because now we're putting some data into phase change memory, saying that that data causes a lot of conflicts. We get better load balancing of the request load. Where are the benefits coming from? Well, we reduce average memory latency compared to frequency-based caching. And that reduction is significant. And again, the reason is better caching and less data movement, less congestion. And energy efficiency also improves. I'm going through these relatively quickly because you don't move a lot of data and you do better caching. So this is the big, I think the takeaway in a lot of these results is that as long as you can take advantage of the characteristics of the application to do better caching and minimize data movement, you get much better results with a hybrid memory. And I think Moin will talk about that too, actually, because his results are similar. Basically, you get increased performance and reduced data movement between DRAM and phase change memory. That's the reason. This also improves thread fairness, which we will talk about later on. Basically, this is some fairness metric, and we'll talk about the fairness metric later on. But this is basically the maximum slowdown any thread experiences in the system compared to when it's run alone. And thread fairness also improves when you do this data movement in a better way. Because now you have less contention in DRAM and better distribution of data between DRAM and phase change memory. So what does it buy us compared to all phase change memory and DRAM-based system? This is the performance, and this is fairness, and the energy results are in the paper. For some reason, they're not here, but they're in the paper. Basically, this is what happens if you have a 16 gigabyte phase change memory system. That's the performance. This is what happens if you have a 16 gigabyte DRAM system. That's the performance. Again, we're assuming that they're the same. This is different from the results that I've shown. And there is no capacity benefit from phase change memory. If you do a scaling study, maybe 64 gigabyte PCM is a better comparison point here. But we're not going to do that. We're going to assume that we have same size. And this is where our mechanism takes us in between phase change memory and DRAM. Basically, there is approximately 30% performance improvement compared to all phase change memory, and approximately 30% performance degradation compared to DRAM, all DRAM. So it's not that bad. Assuming that you get capacity benefits, this will be much better, of course. Okay, so there are a bunch of other results in the paper, and you can look at the paper. I'm not going to go through this. But I think this is a simple idea that can enable better caching methods that are different, that take advantage of the characteristics of the main memory as you go forward. So basically, different memory technologies have different strengths. A hybrid memory system aims for best of both. But how do you place the data between these heterogeneous memory devices is a key problem. The observation in this work is phase change memory array access latency is higher than DRAM's, but peripheral circuit, which is a robot for access latencies, are similar. And we're going to take advantage of that. We use robot for locality as a key criterion for data placement. Place the data that has low robot for locality and high reuse in DRAM, otherwise placed in PCM. You could actually use this at the software level also. This insight is not just applicable to the hardware level. If you're actually placing data in software in these two different types of memories, and if you have knowledge in software what has better locality and what doesn't have better locality, it's probably a good idea to place the data that has good spatial locality in DRAM, right? Even though we've evaluated things in hardware, a lot of the insights are applicable to other operating system and software too. So this improves performance and energy efficiency over state-of-the-art caching policies. Look, talked about this. Any questions? And I think going forward, other policies are very, very interesting also. How can you get the best of both worlds by developing similar policies? Okay, let's take a look at the other problem. The other problem is how do you actually design efficient DRAM caches or efficient technology X caches in general. It doesn't have to be DRAM again here. Efficient large caches, I should say. Basically, the problem with a large DRAM cache is a large DRAM cache requires large metadata. Tag plus block-based information. So imagine that you have a 1 gigabyte cache and you have 64-byte cache blocks. If you do the math, how many tags do you need? 1 gigabyte is 2 to the 30, right? Yeah, and 64-byte is 2 to the 6. So you have 2 to the 24 tags. And if each of your tags is 4 bytes, let's say, which could be small, then you have 2 to the 26 bytes. And that's 2 to the 6 is 64. That's 64 megabytes, right? 64 megabyte tag store. Where do you place that 64 megabyte tag store? Do you place it over here at the memory controller? Do you place it in DRAM? Well, that may not be a good idea, but we're going to do that actually. But if you place it in the memory controller, if you do the dumb thing, that may not be a good idea because that's a lot of storage, right? 64 megabytes.
But usually CPUs come with those on-chip storage now.
Yes, but they use it for caching, not for managing the cache. That's right. Now we're going to use that store just for managing this larger cache, which is going to be wasted basically. It's not a waste. You could argue that it's not a waste, but it's expensive. And also, if you just put a 64 megabyte store over here, what if you add more DRAM into the system? Right? Again, this is not a scalable store. So we want to have a scalable tag store for this DRAM that's efficient, that basically doesn't waste on-chip space.
When you make it off-chip, then access will take much more time.
That's right. Yeah, that's what we're going to do. But we're going to cache the metadata. So I think you're building the mechanism right now. Okay. Yeah, how do we design this efficient DRAM cache? And I think Moin will talk about this also because he has a similar design in the end that we developed independently. Basically, when you get a load request, you need to figure out whether the data is in DRAM or PCM, right? Which means that you need to have some metadata. Metadata is a tag store. And that metadata actually needs to be somewhere. If it's in DRAM, you access DRAM. Otherwise, you need to access phase change memory. So there are several ideas. Basically, we're going to put the metadata in memory. That's the first step. Because we don't want a non-scalable. Whatever you put over here will be non-scalable. This is the same issue with RAIDer, right? If you remember, we don't want to put the bins as a table, the rows as a table, but we wanted to have a Bloom filter over here. Potentially, you could use Bloom filters to manage this cache also, but that's we have not explored yet. Maybe, but I think that's becoming less interesting going forward. The interesting part is the first part, maybe. That Intel can handle, perhaps. Yeah, but yeah, basically we don't want a non-scalable data structure here. So if you want a scalable data structure, basically the scale of the data structure should grow with DRAM size. So if you store the tags in the same row as the data in DRAM, now you're storing the metadata in the same row as their data, and the structure is scalable because as you keep adding more rows, as you keep adding more DRAM, you're also adding more tags, right? And also there's an added advantage. Data and metadata can be accessed together. Basically, you access the metadata, you get maybe a row buffer miss, but when you access the cache block associated with the metadata, you get a cache block hit. You get a row buffer hit. That's one advantage. Basically, the benefit is no on-chip tag storage overhead. This is scalable. The downsides, now this is the downside you mentioned. Cache it determined only after DRAM access, right? You have to access the DRAM first to determine whether you hit in DRAM. And a cache it actually requires 2 DRAM accesses. And that's a problem. How can you fix that problem? Well, another level of caching, right? Unfortunately, that's well, locality is the thing that makes most systems work. So locality is the thing that makes living in Istanbul work also, perhaps. Although that you have a lot of communication latency, for example, in Istanbul, but I don't know how you can do that. But basically, the idea is we're going to cache the tags in SRAM. We're going to store all metadata in DRAM. But basically, the goal was over here to reduce the metadata storage overhead. But we're going to cache part of this metadata that we're storing in DRAM in frequently accessed in SRAM. And hopefully, that will be the frequently accessed metadata. The SRAM size should be kept small, and the paper has actually some evaluations. You could get away with an 8 kilobyte cache. Instead of a 64 megabyte tag store, you can get away with an 8 kilobyte tag store cache. And it gets actually a significant amount of hit rate. Our results show that the hit rate is about 75% or so. Moin's result will show that it's much higher. I don't know how he gets that hit rate. You can ask him. But it's still pretty good. I think it's probably because of the difference in applications. So the third idea, which is orthogonal, is another idea that we've discussed. How much data do you transfer over? Is it 4 kilobytes? Is it 64 bytes? And there's no one-size-fits-all here. This depends on your spatial locality. Basically, some applications benefit from caching more data because they have good spatial locality. Others do not because they don't have the spatial locality. And when you don't have that spatial locality, this large granularity of data movement wastes bandwidth and reduces cache utilization. So the third idea is having a simple dynamic caching granularity policy. And the idea is, again, simple. It's based on cost-benefit analysis to determine the best DRAM cache block size. We group main memory sets into rows. Remember the idea of set sampling that we've discussed, that we've used in memory-level parallelism and cache replacement? You basically have some memory sets, some memory rows or some row sets follow a fixed caching granularity, let's say 64-byte caching granularity. Some other rows follow 1 kilobyte. Some other rows follow 2 kilobytes. Some other rows follow 128 bytes. And you determine the best of those based on sampling, and the rest of main memory follows the best granularity. So we're going to use the same idea. Remember when I told you that, when I discussed that, I told you that this is a substrate for building different cache optimizations. And we're going to use that substrate such that the main memory follows the best granularity. This way you can dynamically detect the granularity of movements. It could be 4 kilobytes sometimes, it could be 64 bytes sometimes, it could be, well, we never went up to 1 megabyte, for example, but you could do that too, if there's benefit to that. And the cost-benefit analysis takes into account excess latency versus how many times you cache. And I'm not going to go into that in detail, but you can imagine policies with this. This is performed every quantum. With one quantum, you figure out that the best granularity is 64 bytes. The next quantum, you use that. If in the next quantum you figure out that the best granularity is 4 kilobytes, in the next quantum you use that. And you could do this on a per application basis also. I guess, okay. So this looks at basically how Timber works eventually. Basically, the final design is you have the DRAM row and this is the raw cache in the SRAM cache. When you get a load, you basically check the cache, and if the tag is cached, there's no need to access the DRAM twice. Right? This is the SRAM cache. Cache is determined quickly. And we find that about 70 to 80% of the accesses hit in this cache if this cache is 8 kilobytes. If there's a hit, then basically you just need to access DRAM to get the data. If there's a miss, then the problem happens when there's a miss. Basically, the latencies get exposed if you miss in this tag cache. And then you need to access the metadata from DRAM. Metadata means the tag in the row buffer. And then the memory controller needs to check if it's in DRAM or phase change memory. If it's in DRAM, then you cache the metadata over here, and then you access the data. So it takes 2 accesses here. Although you could actually speculatively start the access over here before that check. OK, so let's take a look at our methodology a little bit. This is similar to the previous simulator, but this is a little bit older, so we have a smaller. Our simulator was not as scalable at that time. So we have a smaller direct map DRAM, 512 megabytes, and 8 gigabytes PCM. And this is the baseline caching granularity, 128 bytes. So we evaluated several tag store techniques. One is all SRAM tag store. And this is 8 megabytes because our DRAM is much smaller. But as your DRAM becomes bigger and you need to store more metadata, that increases. This is basically tag store in main memory, in the memory controller. The second is region metadata store. Here, the tag store is part of your DRAM, but basically you allocate a region of DRAM for tags instead of storing the tags with the data in the same row. And we'll see that this is actually not a good idea because you get row buffer conflicts on both metadata and data. And the third one is tags in memory, which is storing the metadata in the same row. And the last one is if you add caching on top of it, caching of the metadata. And this is 8 kilobyte SRAM. This is average across all of the workloads that we evaluated, normalized performance and normalized to the SRAM, which is the ideal in this case. This is the SRAM tag store. Tag store is here. If you do region-based tag store in DRAM, you lose significant performance because you have increased metadata lookup access latency. And you get 2 row buffer hits, once for metadata, once for data. Row buffer conflicts, once for metadata, once for data. If you actually do tags in memory, you actually put the tags in the same row, you actually improve performance significantly. So this is the benefit of locality in many workloads. This is actually a surprising result for me. You get 36% benefit just by putting the tags in the same row as the data. So locality is very powerful, as you can see. And this is what happens if you actually cache the metadata, cache the tags in small SRAM. So you get 23% more performance benefit. So it's not still as good as the ideal SRAM, but it's still reasonably good. And I think Moin will tell you some scheduling techniques that will make it better. So that was how you actually organize the cache. What happens with dynamic granularity? Dynamic granularity improves performance by an additional 10%, basically picking the best granularity. And I don't believe that we have the best algorithm. If you're interested in this, I think there are a lot of interesting potential possibilities to pick what is the best dynamic granularity to move data in a hybrid system like this. And that's an interesting problem. I don't believe people have solved that yet. Ours is heuristic based, and it works basically. It works, and it gets you 10% performance. Because it reduces this channel contention, and it also improves spatial locality. And this basically eventually compared to an SRAM-based system, we're within 6% performance, and we're better in terms of energy efficiency, mainly because of this dynamic granularity changes. Because dynamic granularity saves a lot of energy. Instead of moving large chunks of data, you're moving smaller chunks of data sometimes. Or dynamic, you have fewer migrations, and you reduce the channel contention. Because whenever you're moving data, you actually occupy both channels. And if the processor is trying to access that channel, you have contention. OK. Any questions on this? So I think these are just new works that are scratching the surface of the design space. There could be a lot better policies that can enable much better energy benefits as well as performance benefits. So let me wrap up a little bit. I think there are a lot of interesting issues and ideas from the technology layer to the algorithms layer if you want to exploit non-volatile memory or emerging technologies. I abbreviated everything as non-volatile memory. First is, how do you enable non-volatile memory and hybrid memory? How do you tolerate errors? And that's a problem actually that could be solved in many layers here. How do you enable secure operation? I'll briefly discuss this. And again, that's a problem that spans the stack. How do you tolerate performance and power shortcomings of this memory? And how do you minimize its cost? I haven't got into a lot of other layer solutions, but people have actually designed algorithms that exploit some of this, that try to exploit the performance differences between different types of memories. The second is, how do you exploit emerging technologies? Basically, how can you take advantage of non-volatility in the system? People have used, for example, this fast memory for checkpointing purposes. So if you can have fast memory that's non-volatile, you can checkpoint part of your data quickly. So if you're actually operating at a very low power system, let's say you have a sensor system, and your power supply is not consistent, sometimes you lose power. You can design non-volatile memory that's very close to your chip, and you checkpoint very, very frequently, right? So that you don't lose. When you lose power, you can back up quickly. Right? So I think such applications can be enabled with this kind of technologies. How do you minimize energy consumption? Again, you can reduce refresh power, and we've exploited this. The paper in ISPAS that talks about replacing main memory with STT-MRAM talks about a lot about how to minimize energy consumption. And how do you exploit non-volatile memory on chip is interesting also. Can you make some of your caches non-volatile such that, for example, you can make your system more reliable if your caches are non-volatile, because whenever you get a power loss, you don't lose data that's written into your caches, right? Today, when you get a power loss, normally the processor needs to write that data back all the way to the disk. And if you don't have enough power to do that, then you may not be able to get a consistent state of the system. This is one of the reasons why they also tell you not to plug out your USB drivers, because there may be writes that are being flushed out from your memory into your USB drives, right? Whereas if your caches were non-volatile, if your main memory was non-volatile, that wouldn't be an issue, right? The data would be non-volatile in main memory, and you can plug out your USB drive, and the next time you plug it in, it'll hopefully synchronize and be in a consistent state. So you can have a lot of system-level techniques that exploit non-volatility in many different ways. One thing I'll talk about is the security challenges of emerging technologies. I think that's an interesting problem. Because you have limited endurance, you're actually now vulnerable to wear-out attacks, right? So someone can try to wear out the memory by writing over and over. I think there's several. The other issue is more related to privacy, maybe. Because you have non-volatile data, now data persists in memory after power down, right? You can easily retrieve privileged or private information if you find something. This is also a problem with USB drives, right? Those are non-volatile, and if you lose your USB drive, someone can get all of your information. Now, if you lose your cell phone, someone gets even your main memory information, right? And this is another issue that I will not talk about, but there are information leakage issues. If you have multiple bits per cell, you can actually have information leakage. One can read different bits that they're not supposed to read because you're storing multiple bits per cell. You can potentially prevent that, but this is an interesting issue going forward. And this exists in Flash as well, although Flash is much more controlled. So I'm not going to solve these problems, but people have been exploring online wear-out detection mechanisms, attack detection mechanisms, and Moin has some papers related to this. Better hybrid memory system management is interesting, I think, because that way you can reduce some of these wear-out attacks. And basically getting rid of writes from the phase change memory chips or getting rid of writes that cause these wear-outs is the best option here. If you can minimize the number of writes such that you don't write to this memory, you don't have these wear-out attacks. That could be tough, of course. Here, people have been exploring efficient encryption and decryption of the entire main memory. Of course, the problem over there is how do you do that efficiently, right? Because if you encrypt and decrypt every data that goes into main memory, maybe you have a lot of overhead. And again, better hybrid memory system management such that this data doesn't persist that much is interesting. And if you can design the system such that you can hide the information leakage that happens, that's always a good thing. And we're looking at a lot of these techniques, and I'd be happy to talk later, but we don't have any papers related to this yet. Okay. I think before any questions on this, by the way? Okay. Before I move to flash memory a little bit, I'll just summarize memory scaling with emerging technologies. We've already talked about main memory scaling starting from yesterday. These problems are a critical bottleneck for system performance, efficiency, and I would argue usability also, if the system doesn't scale. Yesterday we talked about tolerating DRAM with many different techniques. Today we talked about enabling emerging memory technologies. The basic idea is twofold. One is replacing DRAM with non-volatile memory by architecting non-volatile memory chips well. This didn't work for phase change memory. This could work for other technologies actually, like STT-MRAM. And we discussed that in this past paper. And hybrid memory systems with automatic data management is another idea that relaxes some of the issues with this, because now you can you have more choice in the system, right? And now you can customize the system also. So we're examining many other solution directions and ideas. In all of these directions and ideas, I think again, hardware, software, and device cooperation is essential. That's true for tolerating DRAM also. And co-design is needed between memory, storage, controller, and software, perhaps. And one other direction that I briefly talked about when we started early on is coordinated management of persistent memory and storage. I think that direction becomes very interesting with these emerging memory technologies. Application also needs to provide hints, perhaps, to manage this non-volatile memory technology that consists of both memory and storage. And that's an interesting direction also. What can you do in the application? How can you redesign the application to take advantage of these different hybrid technologies? And that actually, I guess, that's an easier to emulate system as well. So people have been looking at this from the point of view of partitioning data between flash and disks, but they haven't looked at it between DRAM and hybrid DRAM and phase change memory, for example. Should I keep going? Yeah. Okay. It's not time to take a break yet, right?
20 minutes.
Maybe we'll be done in 20 minutes. I don't have a whole lot to add. I decided to keep today short so that we can have more on Monday.
You can just keep it long.
Oh, right, is that the Okay, I'll continue with flash memory a little bit. This will be a different topic a little bit, but this will be a summary of some of these papers, not all of them, because that's a lot of information, I think. But flash memory is an interesting memory technology because it has taken over. It was an emerging memory technology in the 1990s, and when people were working on that before then, people were saying, why are you working on flash memory? It's not a good technology, right? I think the same comments, some of the same comments we've been getting with phase change memory, people were exposed to that those comments much earlier. In fact, I know some people who were working on garbage collection in flash memory. Garbage collection is basically because flash memory does wear leveling, flash translation layer tries to remap logical pages to physical pages such that each page has the same count for writes, right? So that no page degrades more than others. And garbage collection is when you map out a physical page, you don't immediately make it available to the flash translation layer, and you later collect them because you need to erase a page before you program it in flash. And that erase is a costly operation. You don't want it to be on the critical path. So flash memory does it in bulk. And that's called garbage collection. It's very similar to garbage collection. It's basically a dead page that needs to be erased. And that garbage is collected periodically. And people were working on garbage collection in flash memory in the late 80s, early 90s, or even mid 90s. And they received comments saying that, why are you working on this? It's not an interesting technology. And all of their algorithms right now are very interesting because this technology took over. And all of you use flash in your systems, right? Maybe phase change memory will be like that, maybe not. Or maybe STT-RAM would be like that, maybe not. But that's the benefit of investigating this. So this basically shows how flash memory has evolved over time. And this is from the Flash Memory Summit, one of the presenters from Hynix. And as you go from 98 to 2018, this shows a scaling of flash memory with single level cell and multi-level cell technology. So scaling has been quite exponential, right? If you look at this. This is exponential because the scale is logarithmic. I mean, the curve is exponential. And because of this, flash memory has widened its range of applications. Initially, 64 megabytes. And actually, there are 64 megabyte, I think it's not megabytes, 64 megabit prototypes of spin transfer torque MRAM today. So maybe MRAM will be like that later on, right? If you look at it. This was 1998, right? Now we're at a point, maybe it's even higher now. Multi-level cell devices are at the level of 64 gigabytes, which is quite high. And you can, for example, this laptop has flash memory in it, right? Your laptops probably have flash memory in it. Certainly the cell phones have flash memory in it. The question is, can we actually keep scaling this, right? And this scaling has enabled flash memory to be used everywhere today. Can we keep scaling this? And the problem, I'll talk about several problems. As you put more bits per cell, the scaling becomes more difficult. But more bits per cell enable much higher densities. Today we're at 4, actually maybe 8 bits per cell in prototype flash devices. So you can divide the threshold voltage window into 8 chunks, right? And the second is, of course, the key issue that we've talked about. As you reduce the feature size, even if you don't have multiple bits per cell, your charge reduces. So how do we actually enable better scaling of flash memory? One problem is you actually get decreasing endurance with flash scaling. So your endurance goes down. This is with single level cell. Again, this is from the Flash Memory Summit, which is actually a very nice summit. With single level cell flash memory with some nanometers, this is higher than 50 nanometers. We used to get 100,000 writes per cell. So a cell died after 100,000 writes. With multi-level cell and about 50 nanometers feature size, a flash cell died after 10,000 writes. So this is the endurance is much lower, right? The expectation is that with 3-bit multi-level cell, the cell will die after 1,000 writes. 1,000 is 10 to the 3, right? It's very low. So how can you make this memory operate and scale at the same time? Basically, endurance of flash memory is decreasing with scaling and multi-level cells. And to be able to get this endurance, actually, we've been applying much more error correction today. Even with this error correction, we're getting this bad endurance. And I think going forward, a lot of memory will look like this as you scale the size. So error correction capability required to guarantee storage class reliability. So this is storage class reliability. If you look at storage industry, they define the reliability should be this much. And they have a metric called uncorrectable bit error rate. Basically, this is the bit error rate that's exposed to the system. That bit error rate should be less than 10 to the minus 15. So it cannot be more than 1 errors after every 10 to the 15 reads, for example. That's a pretty strict requirement from the storage reliability. If you want to satisfy this with flash memory, basically you need this increasingly exponential error correcting codes you need to apply. You probably know about error correction. Basically, whenever you read, you check some codes, and if those codes match, then you actually say the read is correct. If the codes don't match, then you need to correct it, right? And that comes with overhead, right? Basically, this is additional overhead, 4-bit overhead for some flash page. I believe this is assuming that, well, I'll show you some results with the overhead. Basically, we need increasing error correction capability. But I'll also show you that this increasing error correction capability will not buy us a lot of lifetime. So increasingly, future NAND flash storage architecture will look something like this. And this is actually what looks like in hard disks today. You have some noisy data. Basically, you read stuff that's different from what you write to it. And you need to do some signal processing on top of it to figure out, oh, is this actually what I wrote or not? And after signal processing, you still get some bit error rate, and you do error correction on top of that. This is how hard disk industry works. Whenever you have a hard disk that that processor over there does a lot of signal processing to figure out, is this actually what I wrote? Or can I actually do some voltage adjusting? In hard disk, it's not voltage, but it's something different. But can I actually do some adjustments such that I can decode the signal to make it much closer to what I wrote, what I've written? And then you apply error correction. And there are many error corrections. Today, for example, hard disk industry use LDPC codes, which are pretty complicated. And today, flash industry uses BCH codes, which are less complicated. And Hamming codes are not enough, actually, anymore for flash. And if you're interested in this, you can actually read about these. These are all commonly used codes. But basically, the key realization is that as you go down here, well, actually from here to here, at least, it gets much more complicated to decode and encode. And even after error correction, you still have errors, basically. But the goal is to keep the bit error rate, this uncorrectable bit error rate, to be less than 10 to the minus 15, such that we get storage class reliability from flash memory. And that's a tough goal, which means that we really need to understand NAND flash error patterns. So this is a tough area to do research in, because there are a lot of flash memory manufacturers that do understand NAND flash error patterns, but they don't expose any of that to academia. So we've decided to tackle the issue and say, we want to understand these error patterns such that we can get ahead of the industry eventually. So initial works that we've done are replicating what industry knows, but they don't expose to anyone else in the world. So some of the results that I will show will be known by the industry, but these are some of the first results that are exposed to academia. Basically, what we did was we collaborated with LSI Logic, which is a flash, not a manufacturer, but flash vendor, I guess. They do the flash translation layer. We developed a test system infrastructure that looks like this. We have an FPGA-based controller that actually controls the flash memories, flash chips that are provided to us. And we've designed Yukai designed the motherboards and the daughter boards. And he's very proud of it, so I'll display what he has. But basically, we can, where are the flash chips? These are the boards, and that's the NAND flash. We can put the flash chips there. And we can actually control this. And this is the NAND controller that we've designed to actually check what kind of errors we get flash memory. These are raw flash chips, where we're going to bypass all the flash translation layer. We're going to control the flash chips directly so that we can get the error patterns. Because if you go through the flash translation layer, it does all the error correction anyway, right? That cannot be done, and although that's easier to do. So we looked at 3 X nanometer NAND flash as well as 2 X nanometer NAND flash that I'll talk about later. So once you have this, now you can look at the usage and error. You can develop error models for flash. And there are several ways flash memory is used. Basically, you start and you do some programming. It's called program erase cycles, right? You basically take a block and you can program it, and then you erase it later on, and then that block becomes available later, and then you program it and erase it. Initially, you have to erase the block. And when you erase the block, that's not perfect. You may not be able to erase it fully. Some cells may still remain at some other state. So we'll call those erase errors. Then you program the block. When you program the block, that's not perfect. What happens is when you program a block, it affects some other block around it. This is called program interference. And this is actually an increase. This issue exists in memory. All memory is very similar. In hard disk, this is called adjacent track interference. Whenever you program a track in hard disk, that affects some other track. And people have developed sophisticated techniques to get rid of that. This also exists in DRAM that we're looking into right now. But basically, when you program a page, another page gets affected. We'll call those program interference errors. You write some data into flash, and you read it, and you get some. You ensure that the data is correct, and you don't read it for a while, and you check whether the data is intact. The data may not be intact, right? Which means that you can get retention errors. This is very similar to DRAM, right? DRAM loses charge very quickly, although not as quick. Not all cells lose charge as quickly, right? That's why we refresh it every 64 milliseconds. Flash memory, probably you would think that it's non-volatile, right? But it does have these retention errors also. Basically, it cannot retain data because it's charge-based memory. And we're going to characterize those retention errors. And in fact, this is the biggest problem with flash memory. So we're going to fix this problem by introducing something similar to DRAM, which is refresh into flash memory. basically, retention errors could be, for example, you can keep the data there for 3 hours and check if the data is correct, right? You read the data. Now, when you read the data, you can introduce read errors also. So there's some coupling between these two errors. It could be because of the read itself, or it could be because of the retention loss. But this is very uncommon, it turns out. And you can change the retention time, right? You can make the retention time 5 years, for example. You can store the data, 5 years later, read the block, and see if it's retained. Yeah.
Really? Does it really retain there?
It does retain normally, but it is very dependent on how close to the end of life you are. I'll show you that if you program the block many times, it loses its ability to retain data because it wears out.
I just experienced that.
Yeah.
It could not retain after 3 years.
So I think, oh, you just experienced it?
Yes, after 3 years.
3 years?
Yes.
Okay.
It is all lost.
Interesting.
Yes, I can just give it to you if you want.
So it may, I think it may be because it depends on how many program erase cycles you've done. So it may be that it could actually be less than 3 years, right? Depending on if you can sustain some number of program erase cycles. What flash manufacturers guarantee is 3,000 program erase cycles, as far as I know.
Not 3,000. No.
It's not 3,000?
Yes, it's not much less. I suppose 100 and 200 at most.
Really?
Yeah.
That's pretty low.
It is WDs. I think Western. What is that? Western shape.
Western Digital? Okay. Maybe you can complain to them and say, maybe that's a bad flash memory, right? Or maybe they don't guarantee anything in some parts of flash memory. I don't know exactly what they guarantee. But for storage class reliability, they guarantee that 3,000. So if you take it to a data center, if you're a big customer, they should guarantee you. Maybe that's the problem. Okay, so we're going to characterize these errors, basically. So erase errors, these are different error types that I discussed. Erase errors count the number of cells that fail to be erased to this 1-1 state. That's the erase state. Program interference errors, basically we're going to compare the data immediately after programming the page and after the whole block is being programmed. So flash memory is programmed in this blocks. So this is a block that consists of many pages. It could be 128 pages. And whenever you actually, like page 0, page 1, page 2, page 3, you basically program page 0 and then program page 1. And the actual programming order affects things also, I will not go into. But whenever you program a neighboring page, you affect the next page. Next page. And that's how program interference error happens. Read errors, we're going to continuously read a given block and compare the data between consecutive read sequences. And retention errors will show that that's the most dominant. We're going to compare the data read after an amount of time to the data written. And we're going to look at both short-term retention and long-term retention. And we're going to approximate long-term retention. We haven't done this study for years, of course. So we're going to approximate it by baking the flash memory in the oven under high. We're going to do burn-in, basically. Otherwise, it would take a long time to collect this data, and we would get rid of a lot of flash memory chips. That's right, exactly. So this is the data that we've gathered based on this. This is PE cycles. I don't know why this didn't come out too well, but basically this is the program erase cycles the flash memory has endured on the x-axis. This is a row bit error rate that we see. Lower is better, of course. And this is the different types of errors that we see. Basically, this part, so PE cycles, as program erase cycles increases significantly, the retention errors become more dominant, as you can see here. So these are the, let's pick something here. Basically, the first trend is row bit error rates increase exponentially with program erase cycles, because again, this is a log scale over here. The second conclusion is retention errors are the most dominant. So if you look at 1 year retention time, 1 year retention errors, at this point, at 10 to the 5 PE cycles, program erase cycles, after enduring that many program erase cycles, most of the errors are retention errors. 99% of all the errors that we've seen are retention errors. In the early part of the flash memory lifetime, retention errors are still dominant, but not as dominant. Right? But as you get closer to the end of the flash lifetime, as you do more program erases, retention errors because you wear out the cell and the cell doesn't retain data anymore. You need basically retention errors become much more dominant. And the second type of errors is this one, which is, oh, that's also retention errors. Program interference errors is the next one. I'm not going to talk about that, but we have some analysis in that also to, because this will become more dominant once you fix the retention errors. It turns out fixing the retention errors is easy, and we're going to have solutions to that. Fixing the program interference errors will become much more difficult. And read and erase errors are not that significant, so we're not going to deal with that. Retention errors also increase with retention time requirements. And this is obvious, right? If you test whether you retain data after 3 years, you'll see more errors compared to if you test whether you retain data after 1 day, right?
Actually, this is just out of topic, but it's again related. How do you decide the temperature and time relation? That is, you just or the duration that you use just
for baking and
yes,
So we use Arrhenius equation.
Okay.
And
by using that,
you use that also. Okay, yeah, that's commonly used, and actually burn-in tests also. When processor manufacturers design their systems, they want to test whether the systems work well. They do burn-in, right? They basically do the same thing that we do. They increase the temperature and see if the system still operates reliably in their tests. So we do the same thing. Okay, so what is the retention error mechanism? Basically, why do we get these retention errors? So if you look at a flash memory cell, it could be at a voltage state, so that's from 0, let's say, to the threshold voltage. And you can basically this threshold voltage span is divided into threshold voltage windows. And assuming that you have 3 reference voltages, reference 1, reference 2, and reference 3, flash cells that fall between 0 and reference 1 happen to be encoded with 1, 1. Basically, they happen to encode data 1, 1. Flash cells that have threshold voltage between reference 1 and reference 2 happen to encode 1, 0, and dot, 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 right? Basically, you divide the threshold voltage, entire threshold voltage into sub-windows, and depending on where the threshold voltage of a flash cell falls, you know what data it encodes. And you can easily, actually in Flash, you can easily control the threshold voltage you inject. There's a programming mechanism called ISPP, incremental step pulse programming. You basically keep injecting a little bit of charge into Flash such that you can finely tune what kind of threshold voltage you place the cell in, every single cell in. That's how a Flash is programmed. It's an iterative programming mechanism. You keep injecting small pulses of current, and you check whether the flash cell is actually programmed at a particular voltage. So the iteration step is you keep injecting some current pulse, you check the voltage of the cell. And this is done by the flash controller. That's why you can adjust the voltage of a flash cell. So it's actually pretty interesting technology, I think. Although it's very well known how it operates. This is called incremental step pulse programming. So that's how you can place a cell into one of these states, threshold voltage or threshold voltage windows. And why do I have these distributions here? This is basically the distribution of cells in this state. Some some cells that are in erased state have voltage level here. Some cells that are in erased state that have voltage level here. Some cells that are in state 1, 0 have voltage level here. Some cells that are in state 1, 0 have voltage level here. And the key is ensuring that these windows do not overlap, right? Because you're checking whether a cell, when you're reading a cell, you're checking whether the reference, whether the cell is between these 2 references or these 2 references or these 2 references. If the windows, if these distributions overlap, that means that even though the cell was programmed to be 1, 1, you read it as 1, 0. That's the problem. And the problem with retention errors is they shift these distributions. There's a distribution of voltages for cells that are fully programmed, and over time they lose charge because of leakage current, right? And leakage current actually increases with stress that you apply to the cell. What is stress? As you program it more, it's more stressed. Basically what happens is this threshold voltage window shifts over time. And this voltage window shifts over time also because the cells lose charge, right? And this also shifts over time, maybe less. And this also shifts over time. Basically, the entire thing shifts, but at different amounts. Now, if you actually do the read, if you actually do the read again, let's say you use reference 1 as your reference voltage. So all those cells whose voltages shifted beyond reference 1, they'll be read as 1, 1, even though they were programmed as 1, 0. Right? That's how you get retention errors, because you lost charge on those cells. And what we found out is that cells with more programmed electrons suffer more from retention errors. If you're in this state, you're more likely to lose charge. And threshold voltage is more likely to shift by one window than by multiple. So it's easy for a cell to jump from this state to this state. It's hard for it to shift from here to here. This is also value dependent. Well, this is a value dependency, basically. That's what I described. Retention errors have value dependence. Cells with more programmed electrons tend to suffer more from retention. Yes?
I need to change.
Oh, you need to change that? OK, this is a good place to do that then.